Hello, in this section we are going to study the geometry of first order differential equation. In this section we are going to sketch the solution curve. So firstly, let's take a look at the definition. Okay. So first order differential equation, in the last class we studied the definition. So here is like first order differential equation. This is general. Okay. In the last class, I gave you the general differential equation, nth order, like a polynomial, right? But first order means we don't have second order, third order, we only have the first order. So this is like the y prime just equals the capital F on the right side. So here's the general equation for the first order. So we have some like this one, this one, y prime equals 2x, y prime equals y minus x squared. Okay, they are all called first order differential equation. Okay, and let's see, what's the solution curve? What's the meaning of that one? Solution curve means the graph of the solution. Okay, that means the graph of any solution to the differential equation. dy over dx equals fxy. Let's take a look at example. Example, how to sketch the solution curve. Example 1. So we are going to find the general solution to this one, differential equation. Find the general solution to dy dx equals 2x. Actually, we did this in the last class. Find the general solution. And here, we want to also sketch the corresponding solution curves. Let's take a look. So first question, we want to find the general solution. So how to find general solution? We do the integration. So y equals do integral of our differential equation. So it should be x squared plus c, right? C. And because it's a general solution, that's why we have c. And let's sketch the curve. So this is the general solution. Now we know this is one variable function. It is in plane. Actually, if we make c equals 0, you can see this is a parabola passing origin, right? So parabola like this. If c equals 0, that means c equals 0. If c equals 1, that gives us this one, x squared plus 1. And so, as c is equals 2, x squared plus 2. And if c is negative, that is the curve, right? So all those curves, this is family of parabolas, and they are called solution curve to the general solution. Okay, to the general solution. So there's no specific curve. If we give the initial condition, we can fix the c, then that's a specific solution, specific curve. But right now, just general is a family of parabolas. Okay, family parabolas. And now let's try one exercise problem. Okay, we can try one exercise problem. So we are going to review what we did in the last class. Okay, verify the given solution defines an implicit solution. Okay, verify the given function defines a solution to this one, y prime equals negative x over y, and the given solution, okay, here's this one, x squared plus y squared equals c. This is the implicit solution actually, right? And do you remember how to verify this is given, how to verify this solution? We do implicit differentiation, right? So let's see. Okay, let's have a quick review. Differentiation, implicit differentiation, 2y, y prime. First side is 0, solve this for y prime, so which is negative x over y. This is the solution to that differential equation. Now, the second question, we want to sketch the solution curves. Okay, please try this by yourself. So what's the solution curve to this one? You can see actually x squared plus y squared equals something that is circle, right? And C, given C different number, that means all circles with different radius. Is that correct? For example, C is 4, x squared plus y squared equals 4. That means circle with radius 2. So those are the solution curves. Okay, that's the exercise problem. Let's take a look at another one. Okay, number 3. Exercise problem. Actually, this is a solution to this differential equation. Okay, and we want to find if the initial condition is given, if this is the initial condition actually, okay? We can use the initial condition to fix the C, right? So label the solution curve. We want to label curve that satisfies the initial condition. Okay. Satisfy the initial condition. Let's try this one. We just want to sketch this one. This actually, if C is general, y squared equals x, we can sketch this first. So it's parabola, but it's open this way. And with C different, okay, not shifting, C different, so you can think about y squared equals 2x. So it's just like open up. Something like that. So the familiar curve looks like this. And right now it satisfies the initial condition. We plug in this initial condition into that. So it's y1 equals what? C times 1, which is C, and it is given by 2. So that means y squared, C equals 2. Y squared equals 2x. And this is the solution satisfy the initial condition. And if this is y equals x squared, this is y equals 2x squared. Okay, then that is this curve. Then this is the curve we want. Okay, specific solution curve. That's the definition and the example. Next, we have a definition. It's called the slope field. So a lot of definitions in those two sections. Slope field. So firstly, we know what is slope, right? Slope is what? Slope is the derivative of a given function. How to think about Cat 1? Given a function, how to find the slope? That's the derivative of the function. So slope field means given a function, we can find all the slopes, and each slope give us a field. I'm going to show you how to draw graph. And now let's do the definition first. Okay, let's see. If you learned Calc 4 in the last quarter, we draw the sum graph of vector field. That's similar thing. So for a given differential equation, it's like for differential equation, dy over dx, which equals fxy, first order differential equation, right? And you can see the right side is just the slope. Okay, it's just slope. So we just want to sketch for each point what is the slope is. Let's see. We compute the value of the function fxy at several points, and then draw some small line segment. Small line segment. And having those values fxy as their slope. And the resulting sketch is called slope field. It's called slope field. I'm going to show you how to do this in the example because it's hard to see from here. But from the example, it's pretty easy. Okay. The right side is just a slope. That's why it's called slope field. Let's see. Sketch the slope field for which one? For dy over dx equals 2x squared. Okay. So the right side is fxy. Firstly, we know for the differential equation first order, the right side is fxy. So we make fxy equals 2x squared. So here there's no y, but it's okay. For some other problem, there may be y. But it's just function in terms of x and y. Now we draw a table because we want to draw several points and some small line segment. So here we say slope. Okay. So here for x and the y, because there's no y, so we don't need to give y value. So we just give x value. If we give x value as those ones, you can choose any number. So here is just like a example, so don't worry too much how we choose those points. You can choose 1, 2, whatever you like, doesn't matter. And the slope based on those one, x0 is 0, and for x equals 0.2, 0.08, and 0.32, 0.72, 1.28, and when x is 2, so the slope is 2. And now let's draw the slope field. Okay. So let's see, when x equals 0, no matter what is y, what's the slope? Slope is 0, right? Slope is 0, and we are going to draw some small line segment. So no matter what is y, so the slope is always 0 for any y. But when x equals 0, slope like this one. And then when x is 0.2, it becomes 0.08, so it's pretty small slope, so something like this. right? And the negative 0.2, same thing, because it's x squared, so they have same slope. So same slope. So we just draw. I should do in the same position, like a negative 0.2 and 0.2. So should it be in the same line, same vertical line, okay? Same slope. And then they start to increase the slope, 0.32. So 0.32, okay? A little bit like that. This should be parallel. Some small, because it's small, it's hard to see, kind of. And then 0.8. Turn a little bit larger, like a larger slope. Same thing here. Okay, so here I should draw, for them, no matter what is y, they have same slope. And yeah, we can stop there. And the 2, maybe slope 2. When x is 1, slope 2. So, but when we draw those at some small points, if we draw the graph of solution, actually the solution to this one is this thing, okay? So at each point, you can see that's the slope. That is the slope. And why we want to learn slope field? Because sometimes if there's no way to find a solution, if we cannot solve for y, we can always use computer to draw the slope field, the right side. And from this small field, you can kind of have some idea what's the function solution, what's the solution look like. It's like approximation of the solution. So we only do this when we cannot find a solution. If we can find a solution, we can just use solution, okay? But here, by using just a slope, if we don't solve this equation, just use the right side, we can have some idea of the solution. This is definition 2. Okay. Definition 3. Equilibrium solution. So equilibrium solution means the solution is a constant. So that means any solution to equals fxy of this form. Constant solution, y equals y naught, and here y naught is a constant, is called an equilibrium solution. To the differential equation. So if y equals y naught, that means what? Means like this. Y equals y naught. For example, if y equals 2, right? It's a line. Sometimes the solution may be pretty complicated. Maybe look like that, look like this. The solution all getting close to y equals 2. So y equals 2 is called equilibrium solution. Equilibrium solution. So just means what's the equilibrium solution? You can just think about it this way. Constant solution. So for example, if we have differential equation like this, -1. So you can see y equals 1 is a solution. Because when y equals 1, the left side derivative of the y is 0, and the right side is also 0, right? So it's like 0 equals 0. So you just make the right side equals 0, solve for y, and if y is a constant, y equals 1. So this is equilibrium solution. Equilibrium solution. Equilibrium solution. And I can give you more example like this one. dy dx equals y plus 1 y minus 2. So in this case, we have 3 equilibrium solutions. They are 0, -1, and y equals 2. Right? So that just means equilibrium solution. The last example we are going to do in this section is we are going to find the differential equation by using the given slope curve, by using the given solution curve. Okay, so let's take a look. Determine the differential equation giving the slope of tangent line at the point xy for the given family of curves. So that means given family curves, given solution, general solution, determine the differential equation. Let's take a look at the first one. We have two problems here. Y equals cx squared. Okay, we want to find the differential equation for this one. How do you find differential equation? Definitely we can take the derivative, right? So dy over dx, which is 2c times x, derivative. So this is kind of like a differential equation, but in our differential equation, we shouldn't have c. Okay, we cannot have c for the differential equation. So we want to solve c from the given curve. So c equals, let's see how to solve c, dy by x squared, y over x squared, right? And then plug into our differential equation. So dy dx equals 2y over x squared times x, simplify, which is 2y over x. So this is the differential equation. What's the differential equation? dy over dx equals 2y over x. That's the differential equation. Let's try another one. Okay. Let's try another one. Y squared minus x squared equals c. This is pretty easy because there's no c. For this one, it's just 2y dy dx, but this one is implicit, right? And minus 2x equals 0. Solve for dy dx. dy dx equals 2x over 2y. Is that right? 2x over 2y. Simplify, just x over y. Okay, so for this one, differential equation is x over y. So here you can try this exercise problem. Y squared equals 2cx. Find the differential equation of this one. This is kind of like a combination of the 1 and 2 in the example. Here's the solution. Differentiate to differentiation, implicit differentiation, 2y dy dx, the right side 2c, derivative 2cx is 2c, but we have c, we need to change the c, right? We want to replace c. And then you can solve for dy dx here now. dy dx, which is c over y, but we need to replace the c. Solve from here. C equals y squared over 2x, plug in. Square over 2x and then over y. Cancel the y. So the answer is y over 2x. So that means dy over dx is y over 2x. This is a combination of 1, 2. Implicit differentiation and solve for c, right? So in the homework, you will see the similar problem. And now that's all we need to know for this section. So just some basic ideas of the solution curves. And we know the general solution actually gives us the family of curves. And if initial conditions given, we can fix the particular curve, specific curve, right? So next section, we are going to do separable differential equation. We are going to solve some special differential equation. And we can stop here today.